Welcome to the Tau Performance System talk at the ALCF Inside GPU Hackathon. We have quite a few examples that we will be trying out in the hands-on session. So let's start with the Tau Performance System. We have a workshop tarball that we'll be using, and here are some instructions. If you want to get ahead of the talk and try out the examples, feel free to do that. There's a README file over there. The key question that we are trying to address here is that with growing hardware complexity, it's now getting harder and harder to accurately measure and optimize the performance of our HPC and AI/ML workloads. Our systems are getting quite complex, especially with GPUs. And so Tau aims to deliver a scalable, portable performance evaluation toolkit for both HPC and AI/ML workloads. And I'll show you examples of how we use it with MPI jobs, with non-MPI, just OpenMP jobs, with even Python applications using, say, PyTorch or TensorFlow. So our aim is to deliver this scalable toolkit, and it's a versatile profiling and tracing toolkit that supports many different runtimes. These include MPI, DPC++ SYCL with level 0, OpenCL, OpenMP, even using the OpenMP tools interface for target offload directives. These may be runtimes that you are familiar with and using already, and also Python. It supports scalable performance evaluation of codes written in C++, C with DPC++ with SYCL, Fortran, Python. It supports PAPI for hardware performance counter information, also Liquid, and support for instrumentation for COCOS, MPI, pthread. It supports event-based sampling and many different GPU runtimes. So the key takeaway from this talk should be that you can use a single tool, a tool called Tau exec, to launch uninstrumented, unmodified binaries and immediately start the analysis using paraprof. You can also generate detailed trace files that can be visualized in Ampere, in JumpShot, in perfetto.dev, and Tau's URL is tau.uoregon.edu. So in case you're wondering, how can this help me with the performance engineering of my application? Well, Tau can show you how much time is being spent in each application code region, such as a routine or outer loops. And even within the loops, it can show you what is the contribution of each statement. What is the time spent in OpenMP loops? What is the time spent in kernels running on GPUs? When and where do these kernels get executed? Instead of wall clock time, it can also show you hardware performance counter data from tools such as PAPI and Liquid that can show you floating point instructions, data cache misses, vectorization, etc. What we find is that as we scale up our workloads to larger and larger node counts, a considerable amount of time is being spent in MPI collective operations. But not all of that time is useful. So Tau can show you what is the MPI collective sync time, which is the time spent waiting in a barrier inside an MPI collective operation, and where that takes place in the code. This can be very useful in identifying key bottlenecks in your application as you scale up. It can show you the memory usage, when and where the memory is allocated, deallocated, even the memory footprint of your application, and the high water mark of that memory footprint, the total size of your process memory. Energy usage, I/O characteristics, even the scalability of your application, the efficiency, runtime breakdown across different core counts using the TauDB database and Perf Explorer. So here are the three main components of any performance evaluation tool. There is the instrumentation part where you add hooks to your code. Then there is the measurement part, the measurement module, which includes generating profile files, traces, flat files, call path profiles, and then the analysis phase where you have support for visualization tools such as paraprof or perfetto.dev. Here are the languages that you can use for automatic instrumentation, the different runtimes. and the analysis tools that are provided. Paraprof includes a 3D profile browser, and it also works well with remote visualization, as we'll see in the hands-on session. So here is the instrumentation component, the first and most important part where you add hooks to your code to perform the measurements. Now, while Tau historically has supported source instrumentation using a preprocessor, where you can add the timer start-stop calls in the copy of an instrumented code and then compile it using these special compiler scripts such as tau cc.sh or tau f90.sh, and provide them with selective instrumentation file to filter and reduce the instrumentation focus and narrow it down. We also support other ways of instrumentation. These include not just source instrumentation, but a compiler-based instrumentation, including support for compilers such as Clang compilers or Intel compilers or GNU. And then this instrumentation is added at the function boundaries. And you can use, with LLVM compilers, a special Tau plugin to read a selective instrumentation filter file and include or exclude functions for instrumentation. But you don't need to actually modify the source code or the build system or even the application binary to use Tau, because there is this Tau exec application which allows you to preload Tau's dynamic shared object in the context of the executing application. Using this Tau exec tool, you don't need to recompile or rebuild anything. You just take an unmodified executable and launch it using Tau exec with some options that we'll describe. And then it will preload the Tau DSO and intercept the MPI calls, intercept the calls to the other runtime systems, GPU runtimes, and then it will generate profile and trace data that can be immediately fed to Paraprof, the GUI tool. So after the application executes, you can just launch Paraprof directly and view the performance data and see the profile files. You may require some steps to convert traces if you are using perfetto.dev, which is a tool that comes from Google. So how do you use Tau? First, you must use a module use command to use the soft module files, then load a Tau module, and we have added some new features to Tau that I want to show you. So if you load the Tau2 module instead of the default 2.34 released one, it will give you the latest version of Tau, the GitHub release, where you can easily instrument Python codes for AI applications. You can use OpenMP tools interface with MPI, without MPI, and there are many new features that you may want to see. So for this workshop, we'll use two separate steps of loading Tau. And then you must load the frameworks module to get CMake and Python and other AI tools in your environment. So with this module load commands, you can see that there is a Tau make file which describes how Tau is built with support for, say, level 0, Intel compilers, PAPI, OpenMP tools interface, MPI, and Python, and also one configuration without MPI. So these make files describe how Tau was configured, and you can enable that with selection of these tags that we provide with a -T parameter to Tau exec to choose one of the configurations. Now, it's important to remember that when you launch an application with Tau exec, it will by default use the MPI configuration, this first one. But if you want to use Tau for a non-MPI application, please use the -T tag of serial. Then it will go to the second one, which does not have that -MPI in the tag over there. And it will then load the libtau.so from the shared directory with the name that includes the tags like we see in the MPI name. So it just loads, this preloads this libtau.so, Tau exec will take care of that. And then there are some options like event-based sampling, level 0, that you can then use with, say, Python and other applications. So in short, when you configure Tau with support for, say, Python or MPI library or PAPI, it creates a unique configuration. And each time you configure tau, it creates a unique stub makefile, which is located in the architecture lib directory. It starts out with a makefile.tau name with all these tags which represent how you configured tau. And correspondingly, there is a shared directory where a libtau.so shared object resides. If you were using source instrumentation, you can use the tau compiler scripts like this, and then it will allow you to substitute a compiler name such as MPI F90 with tau F90.sh. And then you can build your application, you can run the application binary and launch pprof or paraprof as GUIs. But again, like I mentioned, if you're using tau exec, you do not need to modify the source code or the build system or even the binary. This is only if you want to do the instrumentation using this compiler or the PDT, the Program Database Toolkit. This is the configuration of tau on another system, say Polaris, where you can see that they are GNU or NVIDIA tags and PAPI, MPI, and so on. And you can put the -t parameter with the same set of tags that you see over here, and then it will pick the configuration associated with that stub makefile. Now, tau supports many different runtime systems. This includes supports for MPI with the PMPI profiling interface, as well as the MPI-T tools interface for using performance and control variables, or pvars and cvars, where you can see what's going on inside the runtime. You can also control the behavior of the runtime by setting some knobs. At runtime, you can say the size of the vbuff pools, for instance, in an MPI implementation, or you can change the thresholds for internal MPI tunable parameters, such as which algorithm is used for the collective communication, or which algorithm is used for the rendezvous or eager protocols for asynchronous communication. We support pthread, we support OpenMP using the OpenMP tools interface, which is now available in Intel compilers, and OpenACC instrumentation, where we can track the kernel execution. OpenCL is supported, as is Intel's One API with level 0. And this allows us to track the time spent in kernels executing on GPUs, and also track the time in One API runtime calls. So if you see the -L0 option, it refers to Intel One API's level 0 runtime instrumentation. Tau also supports the Cocos profiling API. It supports the push and pop interface for regions and kernel execution interface. So if your code is using Cocos calls, such as Cocos parallel for, Cocos parallel scan, Cocos parallel reduce, the first argument that is provided to the Cocos parallel for or any of these calls shows up as a timer in Tau. Tau also supports a large number of other libraries, such as perf tools and perf stubs. And using these timer libraries in packages such as PETC, you can translate the PETC internal timers directly to the perf stubs, which is instrumented and replaced with tau call. So you can see with an unmodified PETC application or a Cocos application, all the internal timers show up in tau profiles and traces, which can make for some very intuitive performance evaluation. Tau also supports Python instrumentation, and recently they have released Python 3.12 with support for very low overhead instrumentation of Python internal routines. So all the Python calls that your application makes, entry and exit of Python functions written by you, show up in profiles using Tau Python as a tool. But I would recommend using that with Python 3.12 and not 3.10, because the instrumentation overhead is significantly lower for that. Now you can also mix and match these configurations. When you configure tau with, say, just MPI with pthread or Intel, one API, or say Cocos with OpenMP or MPI with OpenCL, you can mix and match these configurations and pick the corresponding tau configuration with the tau exec tool. We also have made some progress in binary instrumentation of libraries, and this allows us to actually instrument the application library usage. So if the application was, say, compiled and it was using HDF5, we could rewrite the HDF5 library and not touch the application executable and change the path to use the instrumented libhdf5 like this. And then it will show you the time spent in all the HDF5 functions. With a filter file, you can specify that I am only interested in, say, H5 hash or only H5 routines that start with H5. And so this shows you an example of using the selective instrumentation with tau exec. Tau exec intercepts the runtime and then shows you the time spent in MPI, OpenMP, POSIX.io, and other runtimes. It can also allow you to specify other tau options like event-based sampling, communication metrics, OTF2, and this is how it runs. You have an uninstrumented application. If you run it with MPI run, then you can just say tau exec a.out before the MPI run, after the MPI run command, and then it will show you the MPI performance. If you want to see the performance on the GPU, you can say -L0 for level 0 for Intel GPUs, or kubT ROCm for NVIDIA and AMD respectively, or OpenACC, or OMPT. But this is showing the -T option for OpenMP tools interface. Tau also provides many environment variables. This is setting an OMPT support level to full instead of basic. So you get instrumentation data from all threads and not just thread 0. You can enable tau exec with -IO for tracking IO. You can track memory leaks. You can enable event-based sampling with this, and even hardware performance counter usage, or the resolution at which you should have the instrumentation. We support profiling as well as tracing, where profiling shows you the aggregate data, the summary of all the time spent in each code region, while tracing shows you along a timeline when events take place. With this, instrumentation hooks in the application, with, say, a timer call inside the foo and bar functions, you can generate inclusive time and exclusive time. Exclusive time is the time spent in foo outside of instrumented functions. Inclusive time is this green section all the time in that function. And then you can have flat profiles, a call side profile, call path profile, all the way to traces. You have start and stop timers for direct probes based instrumentation, or indirect via sampling, where if you compile the code with the -G, you get a periodic sample. And this is how it looks. Your application is running, you get a sample, and then it will collect the number of samples where they take place. Sometimes you may miss a code region, say, between these two samples. And this sample can be based on the timer interrupt periodically or using some hardware counter overflow. And instrumentation, on the other hand, inserts a start and stop call in each function and then provides detailed measurements, which results in accurate exclusive and inclusive time. The functions that are instrumented and are lightweight can be throttled away in tau. So if you see a function called throttle, you remember, don't consider its values. It has been, the instrumentation has been disabled after, say, running for 100,000 calls if the time per call was less than 10 microseconds per call. So you get a profile view that shows you the inclusive measurements. You see the value is inclusive here. And a top level timer is called .tau application. Then you can see the function names with the file name and the row and column to row and column. You can see the exclusive time, which shows you the time spent in a particular loop that is instrumented. There are some environment variables you can turn on, like tau trace, setting it to 1 turns on trace files, call path profiling, memory footprint. You can change the size of the call path, turn on sampling, which is the same as tau exec with a -EBS option. Even track signals so you can see a backtrace of where your application crashed. One important option is the tau profile format. If you turn it to merged, then instead of generating a profile file for every thread, it creates a single file called tau profile.xml. You can launch paraprof with this tau profile.xml to view the contents. As you scale up your applications and you're trying to measure the performance of applications at large scales, you may want to use the merged option and maybe even not use sampling at that scale. You can enable tau metrics as well for different counters. This is the view from JumpShot, which is a tool developed at Argonne National Labs, and we are very grateful to them that they have allowed us to ship it with tau as the default trace browser that goes with tau. And here you can see boxes within boxes, and you can see how the communication events are shown with arrows, starting from one process and ending in another. And you can also use the Chrome browser or the perfetto.dev, which is a free browser hosted by Google and developed by Google. The key thing to remember is that after you run your program with tau trace enabled like this, you should merge all the trace files and create a merged tau.trc, tau.event definition file, and then convert these files, these binary files, into the JSON format. There's a tool called tau trace to JSON, and then you give it the -chrome, ignore atomic, and then give a -o for the JSON file. This is the file that you will upload to perfetto.dev. We'll say open trace file over here in perfetto.dev, load this JSON file, and it will then show you thread by thread activity, the flame graph, which shows you the calling order, and then you'll be able to see entry and exit and what happens when along a timeline display. So you can see this MPI wait all is called along this calling path and what it does when the application is waiting here. And this is a GPU thread, so you can see what's happening on the GPU by zooming into a particular segment of this full timeline. This is Vampire, a commercial trace visualizer from TU Dresden in Germany, and it is showing you the COCOS profile. And as I mentioned, the first argument for the COCOS parallel for, parallel scan functions appears over here. So it's very intuitive to see exactly what the application was doing based on those parallel for annotations that were in the code. No change was made to the code. You just set tau trace and export format, tau trace format to OTF2 and run the application with tau exec. And then without any need to merge or convert large trace files, you can simply launch Vampire on the trace file and see the trace visualization. This is paraprof. You launch paraprof, you see MPI ranks along this dimension. This is the total time spent in a code region. If you want to spread it out, you can turn off the stack bars option. Here is the 3D profile browser of paraprof, where you can see along one dimension, the MPI ranks, the functions, and the shape of the full profile. You can even move this function and thread slider to go to a particular point where it intersects. It will show you that the height is 129 seconds and so on. This is available on Aurora, and you can use the 3D GUI as we will all do for hands-on. Where these two lines intersect of the function and thread, you can see the height and color value, which can be chosen over here as the metrics, exclusive time and exclusive time. This is event-based sampling, which shows you along all the MPI ranks, when you launch tau exec with the EBS, which file, which function, which line number was associated with samples that were collected and what they represent in terms of the percentage value. This is an uninstrumented application, but it can show you the exact line where the time was spent. So to recap, these are some environment variables. I will not go into them in detail. I want to focus more on giving you time to try all these examples with OpenMP, with MPI, with Python. And so what we'll do is we'll keep these environment variables in mind for setting different options, but you can do the hands-on next. We have Tau available in E4S Docker and Singularity containers. You can learn more about it at e4s.io, the extreme scale scientific software stack. You can download this from Tau from the Tau website. And there are some reference slides over here for instrumentation and compiler options and runtime environment variables. So let's get on to the hands-on session for the next hour and try it out on Aurora. Now, whenever we want to show GUI tools, you can use SSH-Y and connect to it, but it can be painfully slow over Wi-Fi and rendering it on your own system. So we have set up a remote desktop system. And this is loaded at uooddc.nic.uoregon.edu. You can go to this website, and then you'll see that by default, it's on an admin tab. You need to click here on the Students tab over here. Then you enter your name, your email address, and this code that I have set up for the hands-on. It is 25724. And then you click this login button. This will send you a two-factor authentication code for a secure remote desktop, which is hosted over here. And you will enter that code that you get in the email that you specified here in the next session where it says email verification. You enter this code, and then it will allow you to see this cluster manager. You just click this one link. That's the only link you are allowed to click to Adaptive Computing's HIDE interface in this cluster manager. And you'll see this session 25724. And then you can open this VNC viewer by clicking here. Now, depending on your browser, whether you're using Safari or Firefox or some other browser, you'll have to allow pop-ups from this site. And if I click this Open VNC viewer in Safari on a Mac, I'll watch this area over here, and it comes up with this little pop-up blocker. So I have to click this pop-up blocker, and then it will launch the remote desktop environment on the tab in Safari. It looks like this. This is the first tab. This is the second tab. And then I have a whole remote desktop, which is GPU accelerated. Yes, this is being rendered on a A100 GPU, and multiple people can log in and use this. So when you click on activities, remember, and there's a clipboard over here that you can also use for copying text to and from your host. You click this activities, you will see these 9 dots. You click them, and then you can launch a terminal. Double click on this, it will launch a terminal. You will have this terminal. Right click on it if you don't like the font size, choose the preferences, and then click this custom font, move this slider or change the size of the font. I'm choosing 16 here, click select, and then the size will be a little bigger. Now I have a remote desktop and a terminal window. Here I can go and launch SSH-Y to Aurora using my login ID. This is very important. Use your own login ID at aurora.alcf.anl.gov and use SSH-Y. We also have the E4S container over here. You can find tools like Tau and HPC toolkit all in this when you say Singularity run on this file. But we don't need to do that. This is if you wanted to render it locally. SSH-Y will allow you to log in remotely on Aurora. And then you can say module use soft module files and then load tau with the module load tau and module load tau tau2, like that. Okay, so when you're logging into a remote node, you can then say q sub dash I and then give your account. As I have shown in the other slides, you have to say dash a GPU hack, and the queue is called GPU hack prio for priority queue. And then remember to use the dash X for the GUIs. So this is what you say, dash Q GPU hack priority, and then give the dash capital X option. Then once it goes to the compute node, you can again say module use like this and load all these modules. Then you can use tau very easily by launching an uninstrumented application like this, or instrumented application with tau exec dash level 0 with EBS. Or if it's a Python code, you'll just say Python with foo.py. You may have to say tau exec dash capital T serial if it's a serial code. If you want to install tau on your laptops, here are some instructions. You don't need to. And in short, we'll start with the workshop tarball. We'll launch a remote desktop. We will go to a compute node like this. We'll load these modules, run with an uninstrumented code. We'll look at this README file in the workshop and do this one step at a time for MPI, OpenMP, and Python applications. Here are instructions for generating the trace files using Perfetto. So a lot of this work goes on at the Performance Research Lab at the University of Oregon and Paratools. I would like to thank our sponsors, the Department of Energy, Argonne, National Labs, and the Department of Energy's Office of Science, and Lawrence Livermore National Labs, Los Alamos, Sandia, DOD, NSF, NASA, CEA, Intel, and our partners at different institutions. This work was sponsored and supported by the Office of Science and the Department of Energy Small Business Innovative Research, Innovation Research grants. And you can see our links over here and the exascale computing project. So you have the slides now. I hope you have been able to download the slides. We'll go step by step, very slowly, and start with this. Let's start logging in and going to our UOODDC. And please feel free to write in the text window, in the chat, and also let us go and get access to the system, uooddc.nic.uoregon.edu. Here we'll put 25724 as the code in the student tab. So you click here like this. Okay, so how does that look? So typically you will go here and say HTTPS UOODDC. Do it in a private window if you prefer. And then you'll see this interface. Go click here, students, and give your name and an email address. And then this 25724 and hit login to a training session. Once you click here, it will give you this next screen, which says enter the 6-digit code that you have received in the email specified over here. Remember, once you get a remote desktop, you will be able to launch tools and any GUI tools by logging in remotely. And you could use this for tau, you could use it for HPC toolkit or any other GUI tools. So I hope you are able to do this and you have received a code. I'll wait here for a minute and allow everybody to do that. Remember, go to this website and then click on the Students tab. and put in this code, this unique code, and enter your name and email address and log in. Can I see if, just to put a thumbs up if you are able to log in and you see something like this? You should see this, and then you get an email verification and you enter the code, and then you can click on this Mothra link. Is this okay? Does it work for everybody? Any problems?
Hi, Sameer, this is Marta. Just letting you know that at least from my side, it went well. So
It went well. You could click on this Mothra,
yes,
and then you could open the VNC viewer.
it's connecting, but I think
You would have to open the pop-up window like this.
Yeah.
Pop-up is blocked.
it's working.
It's working. You see a
Jellyfish.
jellyfish like this.
Yes.
Great. Then you can click the activities, click on these 9 dots, find the terminal, double click it, get this. And if you want to change this, font size, go to preferences, resize the font like that, click select, and then SSH-Y to aurora.alcf.anl.gov. When you log in, you'll find that you have a directory like training 16 or something. And tau is already in your path. So if you were to download profile files, PPK files, you can visualize them locally on the system too with the A100 GPU.
Yes, I confirm I was able to follow the steps and it seems successful. Thank you, Sameer.
So you are able to log into Aurora?
Yes, I was able. Yes.
Great. So this is a secure session. Only you can log in with that two-factor authentication. You can say a Q sub command like this, but please use the dash capital X over there. The uppercase X will allow you to launch Paraprof on a compute node directly, and you'll be able to run tau. So this is the workshop tarball that you should untar, cat the README file in the workshop directory, the Q sub with the dash uppercase X, use the GPU hack and GPU hack priority Q. I was able to connect too. Okay, Julian. That's very heartening to know that within a few minutes, others are all able to connect and open a terminal and do this modules. So it's pretty straightforward, right? We'll build applications, we will run them with tau exec, and then we'll launch Paraprof to view the data. I'll wait here for another minute, let everyone catch up. Again, in case somebody missed the instructions, it's straightforward. You just go here. This is slide number 50, and the slides are posted. The link is also in the chat window. Go to uoddc.nic.uoregon.edu, click on the Students tab, enter this number 25724 in this location, email address and name, and then you will receive an email from Adaptive Computing, which has a unique code that you will enter here. And this will allow you to log into this cluster manager. You click here, open the VNC viewer, whether it's Safari or Firefox, enable the pop-ups for your browser. And then you get this jellyfish I hope more people are able to also reach this stage with a remote desktop. If you are able to do this, please give us a sign that you are able to. This is not an in-person workshop, so it makes it easier if everyone is in sync. Was anybody else able to connect and launch the remote desktop? And the clipboard, which you can enable by this button over here on the left side, this is the clipboard where you can cut and paste from your host to the device or from the remote location locally, this clipboard here. Anyone else able to connect? Give us a thumbs up or just please enter in the chat window. I don't want to go fast. Clayton, very good. Julian, great. Anybody else connected? Any problems so far? I'll wait here for a minute. Uh, Someone from Argonne can answer this question. Where is the project space for the project directory?
GPU hack, is that what they're asking?
No, what is the location of the file system, like /project/ GPU hack or something? Okay, found it.
They found it. Okay, it's like lost flare projects and then GPU hack.
Yes. Are you able to untar the workshop tarball and look at the README file and see the examples? We are at the halfway mark for our hands-on session, so we have made good time and we have enough time to do this. You are untarring it, excellent. What about other participants? Is this a blocker? Did you face any problems in reaching this jellyfish? I hope these instructions are clear about where to go, how to click on this, enter this. "25724" is the session code. And then enter your verification code from the email. Click on Mothra and click Open VNC Viewer. And the pop-up blocker. And you should see this screen. Is this okay? Any difficulties with this? Are others able to do this? This will be very useful to you as you navigate all the GUI tools where you can launch them on this remote desktop and have them rendered on this screen. And click here, open up a terminal, and then SSH-Y to Aurora. And then these are the commands for loading the tau modules. Again, they are all over here. After you log in, you can say tar xf. You can cut and paste again using that little clipboard. And this, whatever I will show you, is already there in the README files. In each directory, there's a run.sh that allows you to build and run the application. So it's fairly straightforward. Just remember, as you apply Tau to other larger projects, you should use the Tau profile format as merged and just generate a single Tau profile.xml file that can be launched directly in Paraprof like this. Okay. Here are instructions for tracing. So without further ado, I will just log in. And here is my screen. I had gone through activities like this, clicked on this, chosen this terminal, and then I have this terminal. I did a SSH-Y to aurora.alcf.anl.gov with my user ID, like that. With this -Y. This is very important. Do not forget this. And then I did this qsub command, like I have shown here in the chat window. Okay, so here is the qsub-I interactive, and I put the -X so that I get a remote desktop with the X window support. You can put the wall time to be a little bigger here. You could make it maybe 1 hour, 29 minutes. Just use the -A GPU hack and Q GPU hack priority. Once you do this, you will have a remote desktop with a session which is on the compute node. So here I'll do a tar xf soft perf tools tau tar workshop.tgz. Okay, then I'm going to the workshop directory, and then I can read this README file. Here you can say qsub, just cut and paste this as it is. You'll get a 2-hour allocation with this. And once you are on the compute node, here I'm on a compute node. Here you see tau is not in my path. So here I will just cut and paste directly from this README file these commands. So here I'm cutting and pasting over here. And now I have Python in my path from frameworks. I have tau exec in my path here, and I'm in the workshop directory. So the first thing they are recommending is that I go to this PTI samples directory. Okay, here is the PTI samples directory. There are examples like ZE gem, level 0, OpenMP gem, MPI with OpenMP, MPI with DPC++. This is just without MPI, DPC++, SYCL gem. So let me just start with, say, DPC gem. So CD, MPI, DPC gem. Now what do I see here? I see a README file, is a run.sh, is a cmake lists.txt, and this is the main.cc file. Here is the main.cc, which has MPI and DPC++. Now to build this, I typically create a build directory. I do a cmake ... and then I do a make, and then I can run it like this, MPI exec -n4 DPC gem. Okay. But I've put this all, scripted it up in a run.sh. Here I'm removing, I've loaded this cmake. Actually, cmake may not be needed. I just do this MPI run like this, MPI exec. And then this with dash T, level 0, L0, EBS, and DPC gem. So just say run.sh in this MPC DPC gem directory. And there it is. It is building it. It will run it first without instrumentation, then with instrumentation. And here it is. And in case you are wondering, what is the tau overhead? Let's see that. This is without tau instrumentation. You can see rank 0 of 2, rank 1 of 2 running on the compute node. It's running this GPU kernels. It says without instrumentation, the time taken is 1.84829. And then it runs it with tau exec. And then the time taken is 1.84497. So this is actually with tau, it's slightly faster than without tau, but that's just a small difference. So the overhead is minimal, and then you can see the output from pprof, where you can see where the time was spent. You can see the total time for the execution. You can see the time in MPI finalize, MPI init, samples, and also you can see exactly what happens on the thread 1, where you can see this gem kernel running with level 0 GPU and all of this. Okay. Can you check my question in Slack? Just a second. Let me launch the Slack. And this is the profiler tau. Can I change the prompt in the remote desktop to see the files a little better? Oh, yeah. So yes, this change the font. You can just, say export PS1 equals something like this. And then the prompt changes. So I'll put it in the chat window, export PS1 equals like this. Okay, does that answer your question? Then you will see then you can do PWD. Are others able to reach this point where they are able to launch? Now, remember, if you are in the build directory, you can say paraprof directly over here, and then paraprof, the GUI, will go through this compute node directly to your remote desktop, and you should be able to see a GUI pop up like this. The first paraprof manager shows up, then it loads the file, and now I have thread 1, thread 0. If I click on thread 1, I will see the profile which shows you this GPU like that. And here is the GPU kernel running for 1.7 seconds. I can right click over here. I can say show function bar chart. It'll show me that this was run on node 0, thread 1, and node 1, thread 1. And here is the kernel. So I did not have to change anything in the code. It just shows me the time spent in the kernel running on the GPU. And I can visualize this. I can even launch a 3D visualization, although this is a very trivial test case. And I can see the GUI all running on Aurora and rendering on this remote desktop in real time. I'm on a slow Wi-Fi from the hotel, but I hope this works for everybody. And then you can just try other examples like MPI, OMP gem. And here is again main.cc. Here is the OpenMP target offload directives and run.sh. Here OMP gem. I'm running it with OpenMP tools interface and level 0 and run.sh, just like that. I hope this is okay and working for everybody. It's 1.9555. And here you can see that tau took longer. Instead of 1.94 seconds, the total execution time dilated, and it is now 1.95. Instead of 1.94, it's 1.95. And you can see the target compute on GPU, OpenMP target. You can see detailed information. Here are data alloc bytes, OpenMP target data alloc bytes, transfer device to host, host to device for specific kernels. And the names of the kernels are now expanded. It used to be that the names were very difficult to interpret, but now we have level 0 GPU offloading. And you can see the name of the kernel is compute on GPU with these parameters, and line number is 72. So if I were to look at this main.cc at line number 72, here is the OpenMP target offload directive that it is referring to at line number 72. And if I go to the build directory, I should have paraprof working on this. And really, all we have is just go to each directory and type run.sh. Here is the thread one. And you'll see this is the GPU offloading. And you can then launch the paraprof tool. Okay. Here is some other examples, Aurora callbacks. Now this is with TensorFlow with Keras. Now we have created a example where we do some manual instrumentation. And in this application, this is using Horoward on GPUs. What we are doing is here, TensorFlow with tau, we're importing this tau callbacks. And then we just place this callbacks timers around the Keras tasks. So we say tau callback.tau TensorFlow callbacks. That's it. So the difference between these two, star.py, is we have added import statement and we have added this. And the rest of the code is unmodified. What you will see is that internal timers in Keras, in TensorFlow, their start and stops flow into tau. So if I say run aurora.sh, it is running here, and it will do these epochs over here. And then it will run it with tau instrumentation in the same way. So, okay, let me just go back to this and see if you have any questions about what we just said. Again, just if you are able to log in, and here you can see the epochs running 4 out of 24 and so. So we are using the Intel GPUs for this AI application. And then what I have done is added the one import statement, one callback statement, and then all the entry exits from the internal timers of Keras will flow into tau, and you'll be able to see them over here. So let me just remove star.h5 files and then say run aurora tau.sh. Okay. And here, again, the same application is being used, and we'll see the output. It will do IO here, and we can see the profile files. So please feel free to unmute yourself And let me know, are you able to, first of all, download the file, the slides? Are you able to go to this slide 64? Are you able to log in and use the remote desktop? Do you have this? Are there people who are not able to reach this stage? And what's preventing you from reaching this jellyfish screen? Please feel free to unmute yourself or type in the chat window if you are not able to reach this screen.
Is everyone who is part of the teams trying the Tau? I saw some discussions in the Slack for some of the teams that they're trying it, but I don't know.
Is it difficult? I would love to get some feedback. We have tried to simplify this so that it's easy to get here. And you can see the paraprof launching directly from the compute nodes. As soon as the job is finished, I can launch paraprof and then get the GUI to show up on this remote desktop. Okay, like here. You see these threads? I can click on a particular thread like this and then launch the GUI, or thread 0 for that matter. So you see over here, this is thread 0. And these annotations, training batch 0 taking 21.5 seconds, this is coming from the internal timers of Keras. And so you can see exactly what is going on in the training progress and the times taken for different batches. And Tau exec has minimal overhead. You will be able to generate this data very easily. Here is thread 2. You can see level 0 calls over here. Is thread 1. And you can see all the internal kernels running on the GPU during this execution. You see the gen-conv type info for this ITEX and the gem kernels. This is the kernel that's running. So internal kernels all exposed through this, and then the level 0 profiling and the instrumentation in Keras showing up for the AI example. I have another example here, which is a PyTorch example. Here is a t2.py, and here is a run.sh. So I typically just say Python, which Python, make sure that it's in my path frameworks. So t2.py, I run it like this, right? This is using the Intel GPUs for this PyTorch application. I'll even query the name of the GPU. And then if I want to use Tau, I'll say Tau exec with the -t serial with Python. And then I'm saying level 0 event-based sampling with the Python t2.py. All you have to do is type run.sh like this, ls run.sh, and it will generate the profile files, and then you can view them in paraprof. So PyTorch instrumentation with just no change to the Python interpreter, no change to the Python file. And then here it is running with tau exec, and you should get a profile file that you can launch. So in each directory that's there in this workshop, there should be a run.sh. Just type it and then see how it instruments the code. If you'd like to recap, like me to recap, just log in with instructions, starting at slide 50 from our slide deck. These are step-by-step instructions. And get to a point where you have a terminal window, SSH to Aurora, then untar this workshop tarball, cat the README file. You can just say qsub from the README itself. And then these are modules, just cut and paste that. And you should be all set to go to the examples. They are there in the README file, one step at a time. And each of them has profile files that are generated. Then you just launch paraprof and view them. So here, for example, I ran the run.sh, I have paraprof, and I can now launch paraprof over here. So for this PyTorch example, here are the threads. This is thread 1. I click here, and I can see the kernels running in PyTorch. In detail, I can see how much time the gem kernel took. It took 4.4 seconds in this PyTorch example running on the Intel GPU. And you can see kernel by kernel, all demangled names for all the kernels that ran on the XPU over here. And you can see a 3D visualization of this with all the threads along one axis. Maybe I can expand this and look at the bar plot. And you can see here, this is thread 1. I can use the scroll wheel on my mouse or the plus or minus buttons, the middle mouse button, and I can use the first mouse button to rotate it like this, and I can use the third mouse button to translate it, the right click. Okay. For those who are using the trackpad on your Mac, you can just have 2 fingers pressed on the trackpad and just translate it, or the single first mouse click and you can rotate it. You can see these two. So it's all working well in rendering even 3D graphics remotely. Is thread 2. You can see level 0 calls for host synchronize. And the .tau application is the top level timer.
Sameer, one
So
question. Any of the examples
yes,
has the cocos on that you were mentioning in the presentation?
yes. So whenever you say tau exec on any application, whether it is serial or parallel, it will enable the cocos profiling interface in tau. You will be able to see all the calls with entry and exits, whether it is PETC calling Cocos with PETC timers and Cocos timers, whether it is any other way that you're using Cocos, you will be able to see the detailed information in tau. Here is a TensorFlow application. There's again a README file. And this is from the Aurora documents again. And I can say run.sh over here like this. Okay. And then you can launch Paraprof and view the kernels that ran on the GPU and tweak it. Those who are used to running AI workloads on this, they'll immediately recognize this. Here, the Intel Xeon. Here is thread 1. And you can see the kernels running here. Okay. So we showed with instrumentation that you can get with Keras. You can see what we did for the Aurora callbacks. And then without any change to the Python application, you are seeing all this detailed information on all the nodes. Okay.
Yeah, thank you.
And if I go to PTI GPU again, there are other examples in the samples directory that you could try. Maybe even say OMP gem, which is a serial non-MPI application, is the main.cc, run.sh, and then you just run it. It will build it, it will run it with tau, and you can see the OpenMP. There's no MPI calls here. And detailed OpenMP target offload directives, you can see all the kernel names demangled with the OpenMP offloading. This was something we did with Intel, and they told us how to demangle these names correctly. So you can see all these names of the offloading kernel with line numbers as well, with level 0. Any questions? I'll pause here. We have 15 minutes. For those who were trying it, did these examples work properly for you? Did you face any problems? Did the GUI work okay?
At least from my side, I can confirm that everything worked well. Also running Paraprof. Thank you
Running Paraprof worked? Okay.
Thank you so much, Sameer. There are very great examples, in fact.
Oh, good. And did you try the Windows 3D visualization? Did the 3D graphics work okay with remote desktops?
Try. Can you maybe remind us?
Sure. So, here is an example. Maybe here is a paraprof demo.ppk, a ppk file. You can download it easily with if you're on the compute node, you'll of course need to set a proxy. So maybe we can all just try that. You're on the compute node, set these proxy settings, okay? How do I cut and paste? I take this, I put it in this, I copy it with Command C, I come here, I do this. I did the export, and then I did a wget on http tau.uoregon.edu demo.ppk. I did wget like this. Here's a ppk file. I create a ppk file by saying paraprof --pack and say foo.ppk in a directory that has profile files. Then I can delete the profile files. And with this, I get a GUI like so. So here I can go to Windows. I can see what's happening on this. I can go to the Windows tab and I go to 3D visualization. Okay. So all I had to do was paraprof demo.ppk like this. And then Windows 3D visualization. I want to see the shape of this profile. So I can go to Windows and then I click on this. I get a view like this. I can expand it like that. Okay. And then with the first mouse button, I can rotate it like this. If I go to the bar plot, click on bar plot, I rotate it. If I want to zoom in, then I can just use the scroll wheel or the plus minus buttons. And then I can see the shape. I can go to scatter plot and see the extent of variation. There's one CPU that is different from all these other CPUs, and I'm plotting min to max scales for 4 functions, including MPI barrier here. And I see that 2 of these functions are negatively correlated. What that means is that as the time in this sigma d CQL 3D increases, the time in MPI barrier decreases. And I can see the shape of this. 3D graphics all seem to work okay. And you can see the 2 shapes over here of these 2 functions. As the time in this increases, the time in that decreases. They both are concave and convex. They add up to a constant. And then there is this one thread that is separate. And if I want to zoom into that, I can just go here and then go to this thread. And right here, where these 2 lines intersect, you can see that it took 129 seconds on 199 thread. If I go to 198, it took 8.9 seconds. So at 199, it increases to 129 seconds. Incidentally, this is modeling a reactor, tokamak reactor in this AORSA 2D code, and where this cylinder is processed along a central axis. The CPU that gets this central axis, it does more work, and so its time increases over here. You can see this loop where it happens. And so you can see even in the scatter plot, this is the one CPU that's doing a lot more work in red. So are you able to download this?
Yeah, all went well, at least from my side. I'm playing with the image to understand how it's moving. But at least, yes, I follow your direction and I was okay.
And 3D graphics is working properly for you with the remote desktop?
Yes, the 3D visualization, yes. This image, I don't know how you got it.
I went to scatter plot here in
Okay, because
Windows 3D visualization,
perfect, I have it
and
now.
then scatter plot. And then the other image was with bar plot. And I moved the function and thread slider to reach this intersection point where it was taking a lot more time. And you can see the shape of the entire profile. Instead of seeing line by line text data or data that's, even here I can see half of this machine is light yellow, this is dark yellow. So where the machine intersects the 2 parts of the machine, and concave, convex. I hope others are able to follow along. I understand that sometimes we may not have as much time. You can access this anytime. So this code that I have provided, it will work even tomorrow, next week, or the week after that. I have step-by-step instructions in the workshop tarball and in the slides. So if you are interested in trying it later, that's okay. But I would love to hear if someone tried this and it did not work for them in some way.
Can you say which example you were just visualizing a minute ago? Which
So
example?
this was a wget on a demo.ppk that I just did. So this was not part of the workshop tarball. This is a large application, so I cannot put that. But I can, in fact, if you are interested in seeing this soft cd perf tools tar directory, this is the soft perf tau tar directory, and I can just get this tau.uoregon.edu demo.ppk over here. Okay, so if you wanted to just pick it up from here, you could just say paraprof and then soft perf tools tar demo.ppk, like that. And you can always use this little button here to bring up this, and I can cut and paste from Zoom like that into here. And from here, I can always point it like that in my terminal. Is that okay?
Yeah, that's helpful. Thanks.
Anyone else having problems in launching the GUIs? We have tried to set it up so that all the tools can benefit from this, all the GUI tools, whether you're using a vendor provided tool or one of our research tools like Tau or HPC Toolkit, you can use this setup to log into Aurora and have a responsive remote desktop environment, which can be used for even 3D visualization. You can, of course, always bring this tarball or this PPK file to your local machine as well. Can you just try, Julian, you may not have set up the proxy, and so maybe it's getting stuck. Can you just try this paraprof with this soft perf tools tau, just like this? Just try it from this directory, and you should be able to launch it. And if somebody is interested in trying this on the local machine, even on, say, Mothra, you can always open up a new window over here. And if I said wget with the same URL, tau.uoregon.edu demo.ppk on Mothra, I have it here. And guess what? Paraprof is already in your path. So you can just say paraprof demo.ppk right here, and you'll be able to get it really fast. I can go to File, Preferences. I can change the size of maybe put it in bold, Apply, and then I can launch it. I can go to Windows. This will be much faster, of course, because I'm running it locally. And if I go to the render tab, I want to see what the GL info shows, you will see that this is being rendered directly on the NVIDIA Corporation A100 GPU, not through Mesa OpenGL, but directly on the A100. So this will be really fast. You can feel free to download data sets and run them here on Mothra. But we wanted to make sure that even remotely, it is still performing well. As you can see, this is a lot smoother on the GPU. I hope this works for you and you're able to try our tools. Any last questions? I guess we are at the bottom of the hour. If not, I'll just take this moment to again thank the US Department of Energy, Office of Science, and the DOE labs for their support of the TAO project, the STEP and PESO projects for their support, and ECP. Thanks.